Hello, my name is Nicole Ringo. I am part of Team 5 along with Angel, Alex, and Haley. Today I'll be presenting our experiment, temperature control for a batch stirred tank, effects of proportional band setting for P, PI, PD, and PID controllers. So table of contents. So what will we be covering today, you may ask? Well, first, I'll give a brief overview and introduction, then we'll get a little serious in the ethics, and then move on to our objective for this experiment, followed by the theory, materials and methods, results, discussion, and last but not least, the conclusion. So our introduction. During this presentation, you can expect to learn how basic feedback controllers work, more specifically P, PI, PD, and PID controllers. Essentially, they're used to control an actuator to bring the system to a steady state point. So some applications that these controllers are used for are things like thermostat, heat exchangers, robotics. And a super cool real-life example is the Hard Light VR jacket, which uses controllers for haptic feedback. This stimulates your touch senses for a more realistic VR experience. Moving on to ethics. So here's a real life example of how process controls can be dangerous. So a pesticide reactor pressure vessel at Bayer Corp Science in West Virginia overpressurized and exploded in a runaway reaction back in 2008. So many failures led to this incident. Significant contributors were one, the employers pressuring to get the plant running after a maintenance check, even though the equipment checks, safety review, and the computer calibration were not yet completed. Big mistake. And then second, there was a new control system installed, but operators were not fully trained on how to use it. So the big idea here is that workers relied heavily on the process control system for safety and neglected other precautions. So don't just rely on the software. Be a good engineer. Moving on to the objectives of this project, or of this experiment. Our main goal was to investigate the effects of increasing proportional band in P, PI, PD, and PID controllers, while also determining which controller was most effective in terms of settling and response time for this particular system. So we have 3 hypotheses because we're overachievers like that. They are as follows. 1, higher proportional bands will increase rise time and decrease overshoot. 2, the PID controllers will have the fastest rise time, settling time, and smallest overshoot. 3, we also expect to see an offset present when there is no integral control. So let's dive into the theory. So proportional control, or P control, is our most basic controller type, which works by subtracting the set point by the disturbance, and you get an error signal. And so here is our proportional controller output equation right there. So we got our controller output, PT, our steady state value, our controller gain, our error signal, and our proportional band is equal to 100% over the controller gain. Moving on to the integral control. So it accounts for the area under the error versus time curve, which brings the output closer to the set point. So essentially it's getting rid of that offset. And so here's the integral controller output equation right there. And now on to the derivative control. So it takes the derivative of the error function, and then this allows it to anticipate the future behavior of the error signal by measuring its rate of change, which is why it collapses the oscillatory behavior of P and I controllers, or P and I control. Now, materials and methods. So here is the actual setup of our apparatus. Unfortunately, we couldn't get like a clear image of it, but this is okay. So anyways, but here is a diagram of it. And essentially, so here's this tank, and here are some coils. These are actually cooling coils, and there's a heater inside of the tank. So it's heating up the water inside, and there's water running through these coils and cooling down the water inside the tank. The water in here is also being stirred. And there's a thermocouple inserted at the top. And that thermocouple is communicating to your controller, or to your software, then to your controller, and then it goes back into the system and tunes it out, helps it out, helps it go back to the set point. All right, so how was it done? So first, the cylindrical tank with the cooling coils was filled with tap water. Then the thermocouple, making sure that the thermocouple at the top of the tank was fully submerged in the water. The stir bar was switched on. Room temperature tap water, so 20 degrees Celsius, was run through the cooling coils at a constant flow rate. And then then we set up the software settings. So the proportional band varied with each trial. So at 20%, so we varied the proportional band from 20% up to 40% and then to 100%. And then everything else remained constant. So the trial run time was 36 minutes. The integral time was kept at 15 seconds, derivative time 16 seconds. The set point temperature was 40 degrees Celsius. So it's increasing from 20 degrees to 40 degrees. And then the PSV, which is the valve that allows the water to go through the coils, was initially opened at 50% for the first 18 minutes, and then it was opened 100% for the remaining time of the trial. So after each trial, the tank was drained and refilled with the room temperature tap water. This is to ensure that it stays at that 20 degrees Celsius. And so each lab day, so Wednesday we tested the P and PI controllers, and then Friday we tested the PD and PID controllers. And so we tested each controller 3 times, for the one for the 20% proportional band, the second for the 40% proportional band, and the third for the 100% proportional band. So our results were as follows. So using Excel, we graphed the raw data to plot the temperature profile of the tank. From there, we were able to graph the rise time, settling time, overshoot, and offset. I'd like to add that for the settling time, we defined it as the steady state settling time. So it wasn't centered around the set point. It was centered around our definition of steady state, which was no change within 15 seconds, plus or minus 0.2 degrees Celsius. These bar charts are comparing the offset and settling time of all 4 controllers at varying proportional band settings of 20%, 40%, and again, 100%. So here you can see the P, the PI, PD, and PID controllers. Same here. So this is for the settling time, and that's for the offset. We did the same kind of comparison for overshoot and rise time. Again, we're varying from 20 to 40 to 100% proportional band. And so here you might notice that we only have the PI and the PID controllers displayed. And this is because, as you'll see in the next slide, our P and PD controllers never reached the set point. So there is no overshoot or rise time to measure. On to our discussion. So here you have it, okay? The P controller trials get to a minimum offset value of 6.6 degrees Celsius, and the minimum for the PD was 6.3 degrees Celsius. The average settling time for the P controller was 13 minutes, 10 seconds, plus or minus 0.5 seconds, or I'm sorry, minutes. And then the PD's average was 14 minutes, 57 seconds, plus or minus 12 minutes, which is a huge number. Yeah, we'll get to that in a second. So on to the P and PID. So here our offset values were small enough where we assumed them to be 0. And I'll refer back to slide 9 right here. So this is the offsets. So here you can see like they were barely offset from this set point. Okay. I forgot to mention also that this is where our raw data look like on Excel. And so this is for the PI, this is for the PID. The previous was for P, and this is for PD. So for PI controller, the smallest rise time was 9 minutes and 15 minutes, or 9 minutes and 15 seconds. Smallest overshoot was 0.183. The average settling time is 10 minutes, 50 seconds, plus or minus 0.1 minutes. PID controller, smallest rise time was 10 minutes, 25 seconds. Smallest overshoot was 0.198. The largest overshoot was at 40%, which is kind of not usual. We'll get to that also in a second. And then average settling time was 12 minutes, 38 seconds, plus or minus 0.13 minutes. And another thing to note about the PID controller is that it was very unstable, more so than the PI. So, what did we learn? Well, overall, the higher our proportional band got, it resulted in a higher rise or an increased rise time and a decrease in overshoot. The second one was offset was seen in both P and PD controllers where there was no integral control. So yay, we got those. And then, however, the PD steady state settling time was way too high, ridiculously high. And the PI controller, not the PID controller, was found to be the most effective one in our experiment. And so let's explore why, right? So some things that we believe went wrong was that, so we chose our P, D, and I settings randomly. And so we think that we might have chose very high values for P and or D controls relative to the other settings. The second one was maybe Professor Knight sabotages this experimental data. I don't know, it's just a theory. And then third, there was an external interference picked up by the PD and PID controller. And the reason why we believe this is because D control is highly sensitive to background noise. So we advise future experimentalists to tune the controller prior to the experiment. Don't be like us and just pick blindly. So an example of a tuning method would be the Ziegler-Nicholas method. And this will give you better estimates of the P, I, and D settings to use to test your controllers. And that concludes my presentations. So comments, questions, concerns, love to hear it. Thank you.